Yeah. Okay. So, hi everyone. Welcome back.
Go on.
Yeah. Thanks, Yosef. Okay. Uh, so I noticed that in the last lecture, I was quite quick in the last 5 minutes, and I introduced a new concept, the so-called quadratic forms. So let me just go through them again, the basic definition of what it was, and then we'll finish up all the stuff that I really wanted to say in the last lecture. Okay, so we are dealing with some functions over vector spaces from a vector space to its underlying field, which are essentially abstractions of degree 2 homogeneous polynomials, right? So if you have any degree 2 homogeneous polynomial, you can use it to define a function like this, which satisfies these two axioms. The first one was if you take a scalar multiple of a vector, then when you take out the scale, it becomes a square. And the second is that if you take this thing over here, then it is a bilinear form, a symmetric bilinear form. All right, and because these are basically degree 2 homogeneous polynomials, you can use them to define hypersurfaces or sets of points satisfying a single polynomial equation inside the projective space corresponding to this vector space, right? Because for every non-zero vector, if it is zero for q, then any scalar multiple of that is also zero for q. Now, the conics that we saw in our first lecture, I believe, were also degree 2 homogeneous polynomials. So they are special cases of quadratic forms. Okay, and we are really interested in points inside the projective space. So what we care about are these subspaces of the vector space, or you can say of the projective space, which are called totally singular if all of their points vanish on Q. If Q vanishes on all of these points, okay? And then there's a notion of non-degeneracy as well, which says that if you have a non-zero vector where Q vanishes, then there must be at least one vector such that beta of u comma v is non-zero. And what I will often, the term that I will often use is quadrics. And these are just the points of the projective space where Q vanishes. Right? So this is the hypersurface, this is the collection of points in the projective space. And the main reason why we are interested in quadrics is because when you take the points and lines of a quadric, which means the totally singular points and the totally singular lines in any non-degenerate quadratic form or non-degenerate quadric, then they form a non-degenerate polar space. So this is a big class of examples of polar spaces, which are quite interesting point line geometries that we will use in soon, like in many combinatorial problems. Okay, if that's clear, then finally I ended with the classification of quadratic forms. So this is a big classical result, not just in finite geometry, but it's an important result in algebra. And I'm not going to prove this because that will require me to build up a lot of theory, but I do want you to get comfortable with this classification, to really grasp what this is and what the examples are and so on. So let's just go through this again very slowly. And I noticed I made some mistakes in the previous lecture, so I've tried to correct them. But if there are some mistakes, then I expect all the geometry people here to correct me. Okay, so this is the big classification result for quadratic forms, which says if you have any non-degenerate quadratic form that has rank R, so this is the maximum vector space dimension of a totally singular subspace with respect to the quadratic form. So the maximum dimensional space contained inside the quadric. So say we have rank R and we are working over the finite field FQ in dimension n plus 1, right? So let's just say it. This will then correspond to the n dimensional projective space over FQ, okay? Then there exists some basis of the underlying vector space where the quadratic form has one of these three uh, forms. So it can be written down as these canonical homogeneous degree 2 polynomials. And what are these forms? The first one is known as the hyperbolic form, which has some parameter, which will come in the next slide, where we talk about counting the number of points on a quadric and the number of lines. Then we will see what this parameter is. So ignore this for now. Okay, so the first case is that this dimension, projective dimension n, is equal to twice the rank minus 1. So it's an odd number. And our quadratic form is given by this equation: x1, x2 plus x3, x4 plus x5, x6, and so on till x2r minus 1, x2r. The second case is when the dimension is even, so the projective dimension is even, the vector space dimension is odd. And this is known as parabolic, where again you have the same thing in the beginning, but in the last variable, you have just some constant mu and x square 2r plus 1. And I'm cheating a bit here because I'm not specifying what this constant is. So depending on whether this constant is a square or a non-square, we really have two different parabolic forms. But for our purposes, it won't matter because ultimately we care about the polar space that comes out of these quadratic forms. And for that, it doesn't matter whether this mu is a square or a non-square, right? It's just some non-zero number. I should at least say this thing, right? Otherwise, it's a degenerate form. Okay, so this is known as the parabolic form. And then finally, we have the elliptic form, where again, you have this same thing in the beginning, but in the end, you have the remaining two variables, so x of 2r plus 1 and x of 2r plus 2, they form a degree 2 homogeneous irreducible polynomial. Okay, yeah. These standard forms actually tell you a lot, and we will use them in fact to compute the number of points in a quadric. But already maybe I can ask you some questions by just looking at these forms. So in each of these cases, can you give me a rank R or dimension R singular subspace? For each of these forms, can you tell me like some example of a dimension R subspace which is totally singular, so where Q vanishes completely? Yeah, in the chat, just think about this and let me know if you can think of any example of a rank R subspace. Yeah, I'll just wait for a minute. Nice. So what Yuval says makes sense. For hyperbolic, that's correct. So this was the easier one, right? So you just take x1 equal to 0. Yeah, you just take all the odd xi equal to 0. So xi equal to 0 for all odd I, let's say, right? And that will give you a dimension R subspace, which vanishes completely on them. And what Aditya said, x of 2i plus 1 equal to 0 is the same thing, right? Yeah, for all index I, exactly. So that's a nice example. Exactly the same thing. Now, for these, you'll have to think a bit more, right? That same example which they wrote in the chat doesn't work. So the example is x of 2i plus 1 equal to 0 for all I. This thing doesn't work, but you can think about it and you can actually come up with a similar looking example. It will depend on, yeah, what the values are. Yeah, that's a nice exercise. So in the other two examples, to actually come up with an explicit rank R subspace, yeah, you'll need to put in more effort. But you sort of see what this term is really about, right? It's just a cute thing to observe. Okay. So there are these rank R subspaces. From the equations, you can directly find them. And yeah, here, for example, you can see whether, yeah, you can take this to be 1. Firstly, you can take these vectors 1, 0, 0, and so on. So you have this, yeah, and here you take a 1, and you take both of them equal to, yeah, this equal to 1 and this equal to minus u, I think 1 and minus u, and this, yeah. So you can do this in the other examples also. Just write down some explicit examples. Okay, so that makes it easier to believe that these equations really have rank R. Right? That's the idea. But now the main thing why we care about this classification is because we can use them to count the total number of points. But before that, I have something else. Yeah, okay. Just another observation. If you have a quadric of rank R and the type epsilon that I wrote there, then the dimension of the underlying projective space is 2R plus epsilon. You can check that here. So this minus 1 here, 0, 0, plus 1, plus 1. Yeah, something to keep in mind. And maybe, yeah, it's good to actually go through some examples. Okay, so say we are in the two-dimensional projective space, PG2, Q, then there is only one non-degenerate quadratic form. It's the parabolic one. And the rank is 1. And you can take the canonical form to be xy plus mu z square, let's say. Right? Rank 1 implies it has no lines, it just has points. So this is just a comic. When you go to the three-dimensional projective space, you start seeing different kinds of forms. There's the hyperbolic one, which has rank 2. So it has both points and lines, and which can be written as, yeah, xy plus zw. Yeah. And then you have the elliptic one, which has rank 1, and you can write that as xy plus some polynomial of z comma w, which is irreducible. And this may be, yeah, if you try to draw them in the real space, they basically look like this ellipsoid thingy. So yeah, this sphere sort of a thing. And this one sort of looks like this. You have these lines. You have a grid. In fact, because the rank is 2, this gives you a generalized quadrangle. So this gives you a generalized quadrangle of order q comma 1. We showed that, at least we mentioned that every rank 2 polar space gives you a generalized quadrangle. Okay, and you can go on in higher dimensions. And it's a good idea to basically remember that when the projective dimension is odd, then there are these two possibilities. When it's even, there's just one possibility. That's the main thing to remember. Okay, so finally, let's move on to actually count the total number of points on any quadric of rank R and type this epsilon. And here's a formula which says that the number of points is just q to the r minus 1 multiplied by q to the r plus epsilon plus 1 divided by q minus 1. And the main thing to note here is that this is approximately q to the 2r plus epsilon minus 1. Right, the total number of points in the projective space, so PG of 2r plus epsilon comma q, the total number of points is roughly q to the 2r plus epsilon, and this is the total number of points divided by q. Right. So sort of one dimension lower. This is what happens typically with hypersurfaces, right? Okay, that's the main thing to remember, not the exact formula necessarily, but let's just prove this formula. Okay, so how do we go about this? Well, let f of r be the number of points. Then these are the projective points, right? So these are the non-zero, these are the one-dimensional subspaces which vanish on Q, where Q vanishes. And then this implies that the number of vector solutions to this equation is Q minus 1 multiplied by f of r plus 1. Right? Because every projective point corresponds to these many non-zero vectors. And then the all zero vector is also a solution. Okay. And this thing we can really, we can give a recursive formula for this thing, because remember Q of x is equal to x1, x2 plus x3, x4 plus dot 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 x2r minus 1, x2r plus some f, where this f is either the 0 polynomial, a degree 1 polynomial, or a degree 2 homogeneous polynomial. That's what was there, right? Here f was 0, here it was a degree 1 thing, here it's a degree 2 thing. And from this, you can observe that this thing at the back is just the same quadric, but one rank lower. Right? It's the same form. It's the same sort of quadratic form, but one rank lower. You just remove these things. What I'm saying is this thing is equal to x1, x2 plus q prime of x. Right? So when you want to count the solutions of qx equal to 0, you can count it like this. First, consider the case where this is equal to 0, and then consider the case where this is equal to 1. So when this is equal to 0, there are exactly these many solutions. You have, you have, give me a second. Yeah, okay, let's just say that a bit more. If this is 0, then the total number of solutions is just the number of solutions for x1, x2 equal to 0. And that is twice of q minus 1. So we have 2q minus 1 multiplied by q minus 1 f of r minus 1 plus 1. This is when q prime of x is 0. And when this is equal to 1, then you need to solve x1, x2 equal to 1, or equal to minus 1, sorry. Yeah, you need to solve x1, x2 equal to minus 1. And that also can be solved. Like you can find out the number of solutions, right? For any non-zero x1 that you pick, there's a unique x2. So there also you can determine the number of solutions, and it is q minus 1 times the number of x for which q prime of x is non-zero, which is just q to the 2r plus epsilon minus 1 minus the following f of r minus 1 minus 1. So you find out an equation like you have f of r in terms of f of r minus 1. And you can simplify this to get f of r is equal to q times r minus 1 plus q to the 2r plus epsilon minus 1. If I'm not wrong, I can maybe double check that. I think that's okay. Yeah. Okay. Yeah, I think that's okay, but someone can correct me if it's wrong. Yeah, so this equation, we will interpret this soon in a different way as well, but that's really what gives you the formula, because you can just start with f of 0 equal to 0, the number of points in a zero dimensional, in a rank 0 polar space is just 0, and then plug that in, you get that formula over there. Okay. So now that you have the number of points in a quadric, the next question is what's the number of lines? Or in fact, if you look at it as a polar space, what's the order of that polar space? So what's the total number of lines through each point? And for that, we use this idea that many of you would be familiar with, that from in linear algebra, we have this notion of a quotient vector space, right? So whenever you have a subspace u of v, say this dimension of u is 1 for now, because that's the main thing that we're going to use, then you can define this quotient vector space. You can quotient out u, and that gives you a vector space of one dimension lower, of dimension n minus 1. And you can think of this as geometrically as follows. You take a point of the projective space, and then if you take all of these lines through that point, and say you call them points. So say these things, yeah, each line, say you call it a point. You just define what a point is, and then you take the planes through x and you call them lines. Then the geometry that you get, the point line geometry that you get, is just PG, is just a projective space of one dimension lower. That's the idea, the geometric idea of taking quotient of vector spaces. And for polar spaces, you can define a similar thing, but it's a bit more subtle. And the notion is as follows. Maybe I'll just look at the picture. So here you take a point x of the polar space. So x must lie in x perp, right? We have the isotropic points. These are the points of our polar spaces. And you take all the lines through x inside x perp. So note that x perp is isomorphic to Pg of n minus 1 comma q. So if your whole thing is n-dimensional projective space, then this x perp is a hyperplane. It's an n minus 1 dimensional space inside it. And inside x perp, you take the quotient. So inside x perp, you take the quotient at x. And that, in fact, gives you a polar space of rank r minus 1, so of one rank lower, and type epsilon. So when you went to x perp, you dropped one dimension, and then when you take quotients, so you can note that x perp quotient x is isomorphic to Pg of n minus 2. You dropped two dimensions and you dropped rank by one. Okay. So I'm not proving this, of course, but this is the geometric thing to keep in mind, that for any polar space, you can take these quotients at the points of those polar spaces to get a polar space of one rank lower. Right? And using this, you can actually now see that the number of lines through this point x is just the number of points in one rank lower. It's just f of r minus 1. And from this, you can really interpret this equation as follows. So f of r minus 1 is the number of lines. And on each line, you have q other points, which are collinear with x. That's how you get the first factor. And then this is the number of points not collinear to any x, to this x. So this is the number of points collinear with x in the polar space. And this is the number of points non-collinear to x in the polar space. That's another interpretation of this equation. Okay. And therefore, we see that whenever you have rank r type epsilon, then the order of the polar space is just q comma f of r minus 1 minus 1. So the number of points on each line, because it's a line in a projective space, you have is q plus 1, and the number of points on each line. So the number of lines through each point is this. And the special case of r equal to 2 gives you a generalized quadrangle, which has this order. So in fact, using these polar spaces already, the polar spaces corresponding to quadrics, you get generalized quadrangles of order q comma 1, q comma q, and q comma q squared. Okay. Any questions about this? I'm not really proving that much, so it's a lot of information. But I hope you can internalize some of this information just to see what these objects really are. Any questions? Nope. Okay. If not, then let's move on. Now, in the exercises, it was mentioned and also in the lecture notes that whenever you have a polar space, a non-degenerate polar space of an order, and you take the collinearity graph of this polar space, so the graph on points where 2 points are adjacent if they are collinear, if there's a line of the partial linear space passing through them, then this is a strongly regular graph, right? This was in the exercises, and that's what we really care about. So you can compute the parameters of that strongly regular graph. And again, you can write down exact formulas, but I want to give the essence of these parameters. And the main thing to note here is that you get the number of points equal to just one dimension lower than the number of points in the projective space. And d, the degree of the graph, is just a q factor lower than that. And now the most interesting thing about these collinearity graphs, especially from a Ramsey theory perspective, is that the eigenvalues are quite nice. So the eigenvalues turn out to be roughly the square root of d. In fact, for epsilon equal to 0, you can note here that this thing is just q to the 2r minus 2. So the eigenvalue is exactly square root of d. Well, the order is exactly square root of d. So this tells you that we get optimally pseudo-random graphs. And that's quite nice, that's quite exciting. And also you wouldn't see these examples of pseudo-random graphs in any of the surveys on pseudo-random graphs. What are the two numbers for eigenvalues? What do you mean exactly? You can unmute yourself. Yeah.
So you wrote two numbers when you said eigenvalues. What?
Oh
So
yeah, okay, so the strongly regular graph has exactly three
I
eigenvalues.
see. I
Sorry, I
see.
forgot to tell you that. Yeah, d is the largest eigenvalue. This is the other positive eigenvalue and the negative eigenvalue. Yeah, so this is the smallest one. So qualitatively, they are square root of d, basically. Right? In this case, they are not exactly square root of d. You can check. When I say they, I mean the second largest. You take the absolute value. So remember the notion of n d lambda graphs. I'm talking about this lambda. So this lambda becomes square root of d. You have optimally pseudo-random graphs, and that should make you think that why not use them for the Ramsey theory problem, right? For the off-diagonal Ramsey numbers. We have these optimally pseudo-random graphs. They seem to have some nice looking parameters. Let's use them for Ramsey theory. And yeah, let me say this again. We have epsilon equal to 0. These are the parameters for the graph. And let's observe the following. D is in fact equal to n to the 1 minus 1 over 2r minus 1. Okay, let me write it again. This is twice of r plus 1 minus 3. Does that remind you of something? So recall, if there exists a ks free graph, ks free n d lambda graph with lambda equal to big O of square root d, so optimally pseudo-random, and d is equal to n to the 1 minus 1 over 2s minus 3, then we have solved the big open problem in Ramsey theory. Then the Ramsey number is in fact known. This off-diagonal Ramsey number is in fact some constant times t to the s minus 1 minus little o of 1. That's very exciting. And especially when I first saw this thing, I was like, okay, wow, we have really solved this. And then I convinced a couple of other people also that, oh, maybe we have solved this. But of course, we haven't. These graphs definitely have cliques. They are not chaos free. They have really large cliques. And but that's usually where I thought that okay, that's not a big issue because we saw earlier there was this generalized quadrangle. There was this graph by Coperty that we used to give a lower bound on R of 3 comma t. Remember, we also started with a generalized quadrangle there, and we had a graph that had triangles, but we managed to destroy all those triangles while keeping the graph pseudo-random. So it was still an ND lambda graph, but we could destroy all the triangles. And so that gave us the correct lower bound on R of 3 comma t. So here's the big question for all of you. Can you use this graph to do something similar for s greater than 3? Okay, use this optimally pseudo-random graph, which has the correct parameters. They are generalizations of generalized quadrangles, right? The generalized quadrangle case is a very special case of this graph, in fact. And here is another cool thing. Note that there are no cliques of size r plus 1 in general position, in the sense that the rank of your polar space is just r, right? So this is the maximum dimension of any singular subspace. So you can't have r plus 1 singular vectors, r plus 1 vertices of this graph, which are linearly independent and pairwise orthogonal to each other. So there are no cliques in general position of the correct size. But of course, there are many other cliques. Right? Take any singular, totally singular subspace, take any collection of r plus 1 points in it, that's a clique. But can you do something similar? That's the big question. If you can do it, then you have solved the Ramsey theory problem. That's why I was trying to build up all of this theory and all. So yeah, cool. Any questions about this? Any ideas on how to solve this? Okay, if not, let's move on. So let me end this. I have 10 minutes. Let me end this by a bit more of theory to bore you, but you can think of that Ramsey theory problem if you don't care about this. So this was a question which was also asked in the chat last time, that do all polarities come from symmetric bilinear forms? In fact, do they all come from quadratic forms? And the answer is no, but we actually know where all of them come from. So where all the polarities in PG n comma q, or in fact in general, where do they come from? And this is the general classification of all polarities. So for that, we need another notion of something known as sigma sesquilinear form. Sesqui means 1.5, so they are not bilinear, they are a bit smaller than that. They're 1.5 linear. So this is just a map, like the bilinear forms, from V cross V to the underlying field, such that it's additive in both of these. In the first parameter, it's additive, and also in the second parameter. And the main thing which makes them sesquilinear instead of bilinear is that if you take a scalar multiple of the first vector and a scalar multiple of the second one, yeah, then the first one just comes out of the equation, but the second one gets twisted by this sigma, which is in fact just an automorphism of your field. So you have this field, and every field has these field automorphisms. Some of the fields have only trivial field automorphisms. And so this is known as a sigma sesquilinear form. And these are known as reflexive if beta of u comma v equal to 0 implies the other way around as well. In other words, if u is orthogonal to v, whatever orthogonal means here, then v is orthogonal to u. So it's a symmetric relation. And then the big theorem is that every polarity perp corresponds to a non-degenerate, let's say, non-degenerate sigma sesquilinear form. And it's defined in the same way, right? So if you have U, a subspace, then U perp is simply defined as all those vectors for which beta of u comma v equal to 0 for all u in U. So every polarity comes from these sort of forms. Moreover, these forms have been classified. This is a classical result, I think from 1935 maybe, or something like that, which says that all of these sigma sesquilinear forms, they are one of the following. The first form was symmetric that we already saw, where you had equal to beta of v comma u. The second form is something known as alternating, which has this property. In fact, this property for odd characteristic implies that the following is true. So here basically all the points of your vector space are orthogonal to themselves. And here's an example for you. Beta of, let's say, x comma y vectors, if you want, is equal to x1 y2 minus x2 y1 plus dot dot x of n minus 1 y of n minus xn n minus 1. And these exist only when your n, in fact, this vector space dimension is even. Yes, sorry, Abhishek said characteristic 0 is also fine. Yes, for characteristic 0, for characteristic, yeah, in fact, for non-even, let's say, yeah, my bad. Oops. For characteristic not equal to 2. The implication is also true in even characteristic. The converse implication is only true. Yeah, that's true. Yeah, yeah, that's fine. Yeah. In fact, the implication, yeah, this is actually true for all characteristic. You can just plug in u plus v here, and you get that. Yeah, minus is just a good point. Okay, so here's a canonical example, and in fact, this is the main example you have to keep in mind. Then there are these Hermitian forms where, okay, so in both of these cases, sigma was just the identity, right? There was no twist happening. In the Hermitian form, you have sigma is not equal to the identity, but sigma square is the identity. You sort of need that to have the reflexive property. And you have beta of v comma u equal to sigma of beta of u comma v. And again, let me just give you an example. Let q equal to a square. Then the following thing, x1 y1 to the power square root of q plus x2 y2 to the power square root of q, and so on. This is an example over the finite field, but are there examples of A and B where sigma is not equal to 1? No, in the definition you see that sigma is in fact 1. Yeah. Yeah. So in fact, these are all the examples. Either sigma is 1 or sigma square is 1. So this was a part of their classification result. And here, it's if you have never seen this example, yeah, the main thing to sort of internalize here is that this thing essentially behaves like complex conjugation. So this thing you can see is y conjugate. Because if you have your fq squared, fq contained inside fq squared, or let's write it down nicely so that it fits with what I wrote there. F of square root q is contained inside f of q, then morally, some intuitively this looks like the real number contained inside a complex number. It's a degree 2 field extension, right? So just like you have the complex conjugation, here you have this operation when you raise something to the power of square root of q. This is the conjugation is in fact a good example. I should have given the complex example where the conjugation is a field automorphism of order 2. Okay, so this is a full classification, which is nice. So we really understand all the classical polar spaces. And in fact, here's a table, and this will be the last thing. I will just end with this slide. We can define in the similar way, like we define these quadratic forms, which gave us these polar spaces. We can use alternating or Hermitian forms to get even more polar spaces. And these are all the finite classical polar spaces of rank R in your finite projective space. And to all of these three things also, you can assign a parameter epsilon, which looks a bit funny here because it's fractional. But again, the formulas of the order and also of the parameters of the strongly regular graph can then be written down in terms of this epsilon. So these are all many more examples to play around with or to use in your combinatorial problem, in your Ramsey theory problem or something else. Okay, so I would like to end with that. If you have any questions, then let me know. Yeah. Thanks. Okay, any questions?
Can I ask a question as usual?
Yes, sure.
So you talked about killing off all of the triangles and so on, but I was just curious if you. So let's say you wanted the Ramsey number, I don't know, a million. You wouldn't have to go to the extreme necessarily of killing off triangles, right? You could sort of settle for, if you had medium-sized cliques, for example. I mean, but then you'd have to sort of think about whether, the cliques that were in the graph were smaller than the Ramsey number you were trying to get. I guess it's. Do you see the sort of?
So if you want to make the graph KS free, so yeah, all we did was, we needed a KS free graph to start with. So this S could be a million if you want, that's fine. But yeah, somehow killing all of them is the main thing that you have to achieve, right? If you want to talk about the Ramsey number.
Oh, okay.
For the Ramsey number to get a lower bound, you do need a KS free graph, which has no independent sets of size t. So if you want to show that this thing is greater than n, then you want a graph on n vertices which has no cliques of size s and no independent sets of size t. That gives you the lower bound. So you do need to kill the cliques. Okay, the first three also give optimally pseudorandom graphs. Okay, sorry. First, do you have? I got distracted by the chat. So anything else from you? Yeah, does that make sense?
Yeah, that's good. Thank you.
Yeah. Okay. So yeah, Sam has a question about symplectic and Hermitian polar spaces. I believe they do give you. I haven't checked, but I think this one definitely gives you an optimally pseudorandom graph. I haven't checked the parameters yet. They're all close to optimally pseudorandom, which is good enough, in fact, for Ramsey theory applications as well. I didn't cover that bit, but you don't really need optimally pseudorandom. This was a work of Hay and Victorson, which is in the references, where they showed that you can get away with not having really optimally pseudorandom, but there's a trade-off then in the edge density. And I think these graphs, all of these graphs are potential candidates. So you can just make any one of them somehow clique-free, do something similar that we did with generalized quadrangles, and I think we can then work with that. I think that's a good first step. Yeah, but if Sam calculated the parameters, then you can tell me if they are optimally pseudorandom or not. I didn't check. Any other questions? So I really believe this is not a coincidence. I don't think these parabolic polar spaces with these nice parameters, they are just a coincidence. I really, really feel they should be connected to this optimally pseudorandom clique-free problem. Like I genuinely feel that. I have no mathematical reason for that, but yeah, I hope I have convinced you enough that these are good examples to actually play around with. Like, they have to be. I don't know any other example meeting, yeah, having these sort of parameters. Yeah, wishful thinking, I guess. Okay, so if there are no questions, then yeah, let's take a break. Or is there a question by someone? Oh, okay, yeah, thanks. Let's take a break. Thanks. Yeah. Okay, so let's take a break of 15 minutes and then we can discuss some of the exercises.